In today's lesson, we're going to talk about continuity, what it means for a function to be continuous. To do that, we need to discuss what it means to be continuous at a point or value, say it's c. So a function f is continuous at a value c if the following conditions are true. And there's most books you'll see this, or when you look up the definition of continuity, this is what you'll get. You'll get a three-part definition where the function, for it to be continuous at c, the function at c, f of c, must be defined. The limit as x approaches c of the function must exist. And these two things that we're talking about in parts 1 and 2 must be equal. That is your three-part definition of continuity. So how does this apply? The first example we'll look at is the graph, and it's the same graph that's in the limits unit that you find the limit of. Anyway, we're going to examine the continuity at three values of x: 0, 5, and -7. So first at 0. We're going to examine at 0, which is right here. So let's go ahead and look at the graph at 0. Well, it appears that the function's defined. It's f of 0, if we look it up, is 2. Look up the y value. So f of 0 is 2. Does the limit exist there? Well, if we do the left-hand limit and the right-hand limit, they both are approaching 2. As I approach from the right, it's 2. As I approach from the left, it's 2. So the limit is 2. Also, notice that these are both equal to 0, so these two values are equal. The limit as x approaches 0 of f of x equals f of 0. So the function is, as a conclusion, the function is continuous at 0. Okay, let's look at 5. Well, a lot of things go wrong here at 5. First of all, the function, as you can see, I've written is undefined. Look at the graph. You have an asymptote and you have a hole. That's all you have. No solid point to indicate that the function's defined. So it's undefined. So already we're discontinuous. But I made a note also that the limit doesn't exist here, because if we try to find the left-hand limit here, it appears to be 1, 2, 3, 4. But the problem here on this side, the right-hand limit appears to be negative infinity. So as a result, all three cases fail. But just to reiterate, one case failing, it doesn't matter if it's step 1, 2, or 3, it's discontinuous. So the only time you're continuous is if all three parts of the definition hold true. In this one, all three fail. So as you can see, that can happen. And that will happen when the function is undefined and the limit doesn't exist. Okay, last part, at -7. This one's a little bit trickier. Just trying to get in a little bit closer. That may be as good as we can get. Notice we have a hole at -7, but on both sides of the hole, the left-hand and the right-hand limit appear to approach -4. And I sort of went out of order here. Let me go back to part A. Part A, and by the way, I guess you don't have to go in order. You can do A or B first. The order really doesn't matter. You just have to make sure you do C last. But anyway, the function, is it defined at -7? And actually it is. The hole, you're saying, well, it wouldn't be. But notice we do have the solid point up there. That defines the function. And it appears to be 1, 2, 3, 4, 5, 6. But the limit appears to be -4. We did the little trick where approaching from the right, approaching from the left, we both landed at -4. But the problem is those are not equal. So with what they call a jump discontinuity or removable discontinuity, the first two cases will hold true, but the last case will not be true. And the idea of a removable discontinuity is I can move the point down here and fill in a hole which would make it continuous. But in any event, part 3 of example 1 is discontinuous because part C is not true. Now actually we can simplify this process quite a bit. And as you've noticed, what seems to give us trouble when we're looking at continuity is like if we have a jump or a hole, seems to give us trouble. In addition to maybe, say, a break or an asymptote. Like not part 1, but part 2. So what we can do is I kind of created a little list here. Here's some points of discontinuity that can occur. You can have a break, you can have an asymptote, or a hole. All three of those cases will result in something that is discontinuous at that point. Now there's a term we're going to learn that describes when the graph is smooth. Like this piece of the graph is actually continuous, and this piece is, but at 2 it's discontinuous. So anytime you have one piece that doesn't have any interruptions, or breaks or asymptotes or whatever, we call it piecewise smooth. So if the curve is piecewise smooth, much like this section of the curve, then it will be continuous. But at this point where the break is, it's discontinuous. So I'm going to do another example, and we're going to try a different approach. Rather than go through the 3-part definition, we're just going to look at the piecewise smooth definition of the curve. So, for example, if we look at this one, and I will zoom in just a little bit here. Is there a place where the graph is not piecewise smooth? And the answer is here at 2. Everywhere else the curve is piecewise smooth. So our answer would be the function is discontinuous at x equals 2. So we found a point of discontinuity. That's the only point of discontinuity on the entire curve. So we've kind of simplified the process quite a bit. Let's look at one more example. And notice that they kind of vary on how they ask things. Like sometimes I might ask you, where is it continuous, or where is it discontinuous? Or I might just say at a specific point, where is it continuous? So you can have continuity over the entire reals. They add questions about that. Is the function continuous? And look at the entire graph and tell where it's continuous and where it's discontinuous. But you can also isolate it to a single point and ask, is it continuous or discontinuous? Okay, so determine if the function is continuous at the following points. And here, we're looking at just 0 and 2. And if we go to 0, it appears that part of the graph is continuous. So we would say here, yes, it is continuous. But here at 2, again, we have a hole. I know it's not the best picture of a hole, but it is nonetheless a hole. So the answer would be no. It's not, or you can say the opposite of being continuous is it's discontinuous. Okay, one last example. I wanted to do an example where we're not looking at the graph, but actually the function notation form of it. So as you can see, all these are kind of written as f of x equals g of x equals or whatever. So how do we do it? I guess one way you could do it is that you could graph the function, but there are easier ways to do it. So there's a couple things we can do here. Let's just go through this part by part. One of the things that we're going to find out about continuity is that it will be continuous where its domain is defined. So any function that has a restricted domain where there's places the domain doesn't exist, automatically those points are going to be discontinuous. And that's probably the best way to look at it, but you also think in terms of its graph. For example, A, there's two ways we could do this. One way you could say to yourself, well, what's the domain here? Well, is there anything I can plug into this function that will not work? And the answer is that actually there isn't. Any number I plug in here will give you a function value back. So the domain's all reals. So this would be continuous everywhere. Another thing you could do is graph it. And its graph would be a parabola opening up, passing through the point 0, 3. I'm just going to make a quick sketch, nothing elaborate. But that curve will be continuous. Now B is a different story. Notice what I have. We have a square root. And right away we know that square roots typically can have points where it's undefined. And in this case, we're going to have several. In fact, anywhere, any value less than 3 will be undefined. So the domain here is basically less than 3. 3 is okay. Square root of 0 is 0, so that's defined. So this will be, we're looking for where it's discontinuous. It's going to be discontinuous on, or I should probably say 4. Let's say 4. X is less than or equal to less than 3, not less than or equal to 3. And the last one. Notice we have X in the denominator, so that could potentially create 0 in the denominator, which in this case it will. This function is undefined at -2, so therefore it's going to be discontinuous at -2 because it's undefined at that point. So there are some examples of where you can actually look at the function and determine its continuity, and all is based on where it is either undefined or undetermined. So in this case, this function is defined everywhere, so it's continuous everywhere, and of course its graph is piecewise smooth. And here, this function is not defined when x is less than 3, so it's discontinuous when x is less than 3. And here, it's undefined at -2, so it's going to be discontinuous at -2. An example of, I mentioned the undetermined point would be like this, where you have a reducible function. Notice that to the side. We work those in the limits unit, where it reduces down and you can evaluate the limit. So the limit does exist here, but it's discontinuous because it's undetermined at that point. Okay, continue the work. Assign problems and problems out of the textbook, and email me if you have any questions.